Hello. In today's video lecture, we're going to be talking about unit cell calculations. And for our unit cell calculations, we are going to be looking at them for both metallic or atomic and for ionic. So we're going to look at density and packing efficiency of both metallic cells, unit cells, as well as ionic unit cells. Okay, so with our density, we're looking at mass over volume. And since we're talking about a unit cell density, we're talking about the mass of atoms in unit cell divided by the volume of the unit cell. Since we are talking about a solid, this is going to be grams over centimeters cubed. Okay, so we're going to be looking at atomic cells. So atomic or metallic densities. And of course we're going to be also looking at ionic, but let's start with that. So here we're going to take the mass to be the mass of all the atoms within there. And they're all going to be the same, so we have just one single Z, which is our number of atoms. Multiply that by our molar mass, which is going to be in grams per mole. And then we're going to multiply it by the reciprocal of Avogadro's number, which will give us, let's make this a little more clear. It'll be 1 mole divided by 6.022 times 10 to the 23rd atoms. And when we multiply all this out, we'll cancel out our atoms. We'll cancel out our moles, and we'll be left with grams. But we'll be left with the amount of grams we have for just the number of atoms we have. Our volume, remember we are dealing with a cube, right? These unit cells are all cubes. So we have length, width, and height all being the same. So we're just going to take our edge length, which we call A, and we're going to cube it. And this will give us centimeters cubed. So keep in mind that A must be in centimeters. Okay, so you may need to do some calculations in order to complete that. So let's try a very quick example. So let's take iron. So iron is a body-centered cubic, and it has an A value equal to 2.866 angstroms. We want to know what the density. Okay, so if we have BCC, we have a Z number of 2. So our mass, or we take 2 atoms, multiply it by our molar mass, which is 55.85 grams per mole. Take the reciprocal of Avogadro's number, and we get our mass as 1.855 times 10 to the negative 22 grams. We then divide that by our volume. So we have 2.866 angstroms. Hopefully you remember that there are 10 times, well, we could do it, I'm actually going to do it as 1 times 10 to the negative 10 meters per angstrom. And then we want to go from meters into centimeters. So there are 100 centimeters per meter. So that'll get us from angstroms into centimeters. We're going to take that whole thing and cube it, which gives us 2.345 times 10 to the negative 23rd centimeters cubed. And then when we divide our grams by our centimeters, we get a density of 7.880 grams per centimeter cubed, which is a reasonable solid density. Okay, if we want to look at an ionic cell, we just have an additional type of atom. So we have a cation and an anion. So our mass here will be equal to our Z plus, so our cation number of atoms, times by our grams per mole of our cation. Still use our molar mass, but just for our cation. And then we use Avogadro's number. Okay, and then let me just move this actually a little bit over. There we go. And then we're going to add that to our anion coordination, or anion Z number, times by our molar mass of our anion. And again, Avogadro's number. And then we'll all divide that by A cubed. Okay. Some notes about your A for ionic cell. A well, really, just in general. A comes from, or sorry, A can be calculated. Sorry about that. Using the R or R minus, whether we have an atomic or a anionic cell. So A will be related to R. Like so, if we have a primitive cubic. If we have a body-centered cubic, A will be related to R using A is equal to 4R square root of 3, or A is equal to 4R minus square root of 3. Lastly, for our face-centered, A is equal to 4R square root of 2, or A is equal to 4R minus square root of 2. So you can relate A and R using these formulas, and R is your radius of either, so R is your metallic radius, and then of course R minus is your anion radius. Okay. For the relationship between A and R minus, it's not quite as good because with the cations in there, that could cause some expansion of the cell, but just keep in mind that if you need a nitty-gritty way of comparing the two, you can do this. Okay, next we're going to look at packing efficiency. So our packing efficiency is going to be the volume of our atoms in our cell divided by the volume of our unit cell. Okay, so of course we're going to have an atomic variant and an ionic variant. Our atomic is going to be our Z number. Times by the volume of a sphere. Okay, and this will give us these two together will give us the volume of our atoms in our cell. And we're going to divide this by A cubed, which will give us the volume of our unit cell. Keep in mind, as long as R and A are in the same unit, it doesn't matter what unit you use. Okay, unlike above where we needed to have specifically centimeters, here we can be in centimeters or nanometers or angstroms, whatever we want. For our ionic, we again have two different types of atoms. So we have a Z plus times by 4 pi R plus cubed. So we take our cation radius divided by 3. And that whole thing is added to our Z minus times by 4 pi R minus cubed. So the radius of our anion. Sorry. And there we go. And we're going to take this whole thing and we're going to divide it by A cubed. Okay. Just want to make some notes about all of our calculations. Well, let's real quick. Packing efficiency. A note about packing efficiency. All our metallic cells, all of the ones that are primitive will have the same packing efficiency. All of the ones that are primitive, body center cubic, or face center cubic will all have the same packing efficiency. So our packing efficiency, actually, so our packing efficiency for primitive atomic cells will be 52%. For body-centered cubic atomic cells, 68%. And then for face-centered and hexagonal closest packed, 72%. So just as a note, no matter what type of atoms you have, if you're an atomic cell, you will have set packing efficiencies. Our ionic cells will be different though. Okay. Some additional notes. Z, that is the number of atoms in an atomic or metallic cell. Z plus is going to be the number of cations in a unit cell. Z minus number of anions in a unit cell. Okay. Z does not tell us our empirical formula. Our empirical formula will be taken by dividing by the largest common number that you can come up with, so you can get the smallest whole number ratio. So remember, this is the smallest whole number ratio. So we'll take our Z plus and our Z minus and get our smallest whole number ratio, and that will give us our empirical formula. Okay. Also, keep in mind our metallic solids will only have one Z type. So no Z minus, no Z plus. And it'll be based upon the packing of our unit cell. Right, so our unit cell packing types for metallic are primitive or simple, body-centered cubic, or face-centered cubic, also known as cubic closest packed. Ionics are going to have Z plus and Z minus. Keep in mind also, our anions themselves are what's going to form our unit cell, and then we're going to shove cations in the spaces left over. Okay, so anions make up the unit cell. That means that they are going to be forming primitive body-centered cubic or face-centered cubic arrangements. Of the anions. Okay. And then cations fill interstitial holes left over. So remember our packing efficiency up here. If we have a simple or primitive unit cell, we have 48% of that cell that's left over and empty, that doesn't have any atoms. So those cations will fill that within a unit cell, or a ionic unit cell. We have 68 in a BCC, so we still have 32% of the cell that's empty, ready for some atoms, or cations in this case. And then here we have 28% of the unit cell that's left over that can be filled with cations. So that's why our packing efficiency for our atomic cells will be this, but since we have cations, we can shove it in those spaces that have not been taken up by the anions. Okay. So, these interstitial holes, which we're going to talk about in a further video, they are cubic, tetrahedral, and octahedral holes. Okay, it'll be based on size. So we'll look at all of that in a further video. Bye, y'all.